Let's talk about the null space and image of a matrix. So the null space of an m by n matrix is it's defined like this. It's all of the vectors in Rn, so that when you multiply on the left by A, you get the 0 vector. Okay? Now it's not totally obvious that this actually is a subspace, so let's just check. Remember, we have three things to check. First, we need to check that 0 is in this collection of vectors. So if we have a matrix A and we multiply by the 0 vector, do we get the 0 vector? Well, yes, clearly. These 0 vectors might have different numbers of entries, right? The 0 vector on this side is going to have n entries, and the 0 vector on the right is going to have m entries. But when you do matrix multiplication, if you started with zeros, you're going to get all zeros. So 0 is in this null space. Okay, the second thing we need to check is if we have a vector in the null space, is any multiple of it also in the null space? So let's check. Let's take a vector in the null space. That means that if you multiply v on the left by a, you get the 0 vector, right? That's what it means to be in the null space. Well, now we need to check is, if we do any scalar multiple, will that be in the null space? Well, let's check. If we multiply this vector on the left by a, do we get the 0 vector? Well, remember, matrix multiplication associates and commutes with scalar multiplication, so we can move this scalar out front and stick parentheses over here. But a times v, we said, has to be the 0 vector, so this is c times the 0 vector, that's the 0 vector. So c times v is in the null space. All right, one last thing to check, and this one is slightly trickier. We need to check if sums of vectors in the null space are in the null space. So let's take two vectors in the null space. We need to check, is v plus w in the null space? How do we check that? Well, how do you check if something is in the null space? You multiply on the left by the matrix and see if you get 0. So we need to check, is this 0? Well, the only thing we know about anything here is that v and w are in the null space. So let's try to get that knowledge into the game somehow. We can distribute a. It's really the only move we have available. So hopefully it's helpful. But v is in the null space of a, so a times v is 0. But w is in the null space of a, so a times w is 0. And 0 plus 0 is 0. So the null space is closed under vector addition, it's closed under scalar multiplication, and it contains 0. That means the null space really is a null space. All right, what about the image? Well, the image of a matrix is defined by the matrix times any vector that happens to be in Rn. Another term that sometimes gets used is the range of A. And so this is very much, we're very much treating A like a function, right? The range of a function, if you have a real valued function, the range of a function is all of the vectors, or all of the numbers that function hits, right? Well, it's the same here. The image of a matrix is all of the vectors that matrix hits when you do matrix multiplication on the left with that matrix, right? So how can we show that this is a subspace? Well, we could check the same properties, but I'm going to do it a little differently. So x is going to be x1 down through xn. Right? And it has to be xn because x is in Rn here. But remember that matrix multiplication like this, or a matrix times a vector on the right, really gives you a linear combination of the columns, a linear combination of the columns of this matrix. So what we get is x1 times the first column all the way through xn times the nth column, right? So this collection of all vectors times A is the same as the span of the columns. So the image of A is actually the same as the column space of A. Right? So since the column space is a span, the image is also a span, and therefore it must be a subspace. So it may seem strange to have two different names for exactly the same thing, but the reason for this is, conceptually these are different. So column space is just a span. It's just a span. But image, we'll see the image is really, we're treating A like a linear vector function, and the image of a matrix is then the image of that linear vector function. So even though they describe the same collection, or the same subspace of Rm, conceptually they're different. So, all right. Well, let's find a basis for these things. So let's find a basis for the image in the null space of this matrix. Well, we just noticed that the image is really the same as the column space. And we know how to find a basis for the column space of a matrix. Because the column space is in, for this particular one, the column space is going to be in R2, we know how to find the basis for a column space, so I'm going to take a shortcut. The column space is in R2, so 3 vectors have to be linearly dependent, so let's throw away at least one of them. How about this last one? So now the only question is, are the remaining 2 vectors linearly dependent or independent? Well, when there are only 2 vectors, they're linearly independent as long as they aren't scalar multiples. But these 2 vectors are clearly not scalar multiples, and so the basis for the column space is just these first 2 columns, 1, 1, and 1, 2. Another way to do this is, well, the column space, if it has two vectors in its basis, the column space must be all of R2. If it's all of R2, then you can just use 1, 0, 0, 1 as a basis. Okay, but this first way is maybe a little better because it displays a basis for the column space consisting of columns of A, which is maybe better. Okay, so now let's think about the null space. So the null space of a matrix, right, what we need to know is, since the null space of A is all of the vectors that go to 0 when you multiply them by A, we need to think about what sort of vectors appear as solutions to this equation, right? The null space is essentially all solutions to this equation, so let's solve this equation. To do that, we can row reduce A as usual, so 1, 1, minus 3. So we're going to subtract row 1 from row 2, so 0, 1, minus 1, I think. And then just to be super explicit, I'm going to go all the way to reduced row echelon form, so subtract row 2 from row 1, so we get 1, 0, minus 2, 0, 1, minus 1. Okay? Now remember, this we can use this reduced row echelon form to write down the collection of solutions to this homogeneous equation. This says that x1, so we're going to need an x1, an x2, and an x3, right? This says that x1 has to be equal to 2x3. It says that x2 has to be equal to, x2 has to be equal to minus x3, no, plus x3, sorry. And x3 is free because there's no pivot in the column corresponding to x3. So x3 is free, so x3 is just x3. But notice that this is x3 times 2, 1, 1, right? So this right here is x3 times 2, 1, 1. This is the null space. right? Every vector, and x3 can be any real number here. So every vector of this form is in the null space, and every vector in the null space is of this form. But this is clearly a span. This is just the span of the first column. Or I'm sorry, some people call this a basic solution, but anyway, this vector. So the null space is the span of this vector. All right, so we have, and since there's only one vector, it must be linearly independent since it's non-zero, so we have a basis. So the null space here has dimension 1. All right, well, let's think about the dimension of these things. So as usual, we're going to think about how does it work when we do, what happens when we row reduce this matrix, right? We've seen since the image is really the same thing as the column space of A, we can find the dimension of the column space by doing a row reduction, but we can also find as we just saw, we can find a basis for the null space by doing a row reduction, so we can also find the dimension of the null space by doing a row reduction. So let's imagine that we have this matrix A, and we do a row reduction all the way to reduced row echelon form. Okay? Right, we're going to end up with some pivots, and maybe some columns without pivots. Now we know that the dimension of the column space is the same as the number of pivots. It's the same as the rank of the matrix, right? Which is just the number of pivots. But that's the same as the number of non-free variables, right? If we were treating this as a matrix corresponding to a homogeneous system like this, right? The number of non-free variables is the same as the number of pivots. Okay, well now let's think about, so that's the dimension of the column space. Now let's think about the dimension of the null space. Well, what we saw in our previous example is every free variable here, so maybe this is x2, x4, and x5. Think back to your experience of writing solutions to homogeneous equations. Whenever you have a free variable, right, when you write solutions to a homogeneous system, what you get is a free variable times some vector, plus another free variable times some vector, plus, I guess this would need to be a 6, plus another, right? You get some vector times each one of your free variables. But each one of your free variables is, it's free. It can be any real number. So that means that the null space of A is the span of each one of these vectors, right? So where do these vectors come from? Well, I think an example will be worth 1,000 words here. So let me just write a reduced row echelon matrix. How about something like this? 2, 0, 3, 4, 5, 6. Okay. Yeah, that's fine. So we have, here's x1, x2, x3, x4, x5. So those are the columns corresponding to those variables. So x1 is going to be minus x2 minus 2x2 minus 3x4 minus 4x5. x3 is going to be minus 5x4 minus 6x5. Okay, so that means that when we write our solutions, x1, x2, x3, x4, x5. Okay, so we're going to get some vector times x2. What vector is it? Well, this coefficient, right? We need that coefficient right here. But that's the negative of this one. Right? We need, and that's it for x2. I guess we also need x2, 1 times x2 to be x2. And 0's the rest of the place. Okay, what about for x4? So we need some vector times x4. So for x1, we need a minus 3. And this minus 3 is just the negative of the 3 that shows up in our reduced row echelon form. For x2, no x2's. For x3, we need minus 5. And this minus 5 is just the negative of the number that shows up right there. And then for x4, we need x4 to be x4, so we need a 1 here and a 0 there. And then for x5, I'm gonna squeeze it in over here because I have a reason to want these all on one line. For x5, we need a minus 4 here, and that's the negative of that entry. No x2's. For x3, we need a minus 6, and that's the negative of that entry in our reduced echelon form. And then no x4's, and then we need x5 to be x5, so we need a 1 right here. And this is times x5. Okay, well, so this shows that these so-called basic solutions, they do span the null space, which is what I was saying before. But now we need to know, right, are these a basis? Are they linearly independent? Well, look at the rows that correspond to the free variables. x2 was free, x4 was free, and x5 was free. So looking just at these, is it possible that these are linearly dependent? Well, no, because look, they each have a 1 in a different entry and 0's in the other entries. So it's impossible for these to be linearly dependent. These are definitely linearly independent. Right? We don't even need to know what these numbers are in the other rows. Just by looking at the rows corresponding to our free variables, we can see that these basic solutions are guaranteed to be linearly independent. And this always happens. There was nothing special about this particular matrix that made this happen. So how many linearly independent vectors do we get as a basis for our null space? Well, so dimension of the null space, what this shows us is that there's one linearly independent vector in this basis for every free variable. So the dimension of the null space is the number of free variables. All right. So that's interesting on its own, right? Dimension of null space, this gets called the nullity of the matrix. And these two facts together give us a theorem that is surprisingly simple, but also surprisingly important for analyzing matrices. It's called the rank nullity theorem. And the rank nullity theorem just says that the rank of a matrix plus the nullity of the matrix is the number of columns of the matrix. So the rank of the matrix, that's the dimension of the column space, also the dimension of the row space. The nullity of the matrix, that's the dimension of the null space. Right? So how could we prove this? Well, the dimension of the column space, that's just the number of free variables the number of non-free variables. So here, when I say free variables, I'm saying suppose that we had a matrix equation, or a vector equation, AX equals 0, a homogeneous matrix equation, then the dimension of the column space of A is the number of non-free variables in this equation. On the other hand, we just showed that the dimension of the null space is the number of free variables. Right, so what do you get if you add the number of non-free variables to the number of free variables? Well, there's one variable for every entry in this matrix, and the number of entries, number of entries in this vector, and the number of entries in this vector is n, because there has to be n entries in this vector for this product to even be defined. So these have to add up to n, right? So this is, when you translate this into the language of a homogeneous equation, this says that the number of free variables plus the number of non-free variables is all of the variables, which is obvious when you say it that way. But when you interpret it in terms of the image and null space of the matrix, it tells you non-obvious things about the dimensions of those spaces. So that's why the rank nullity theorem is surprisingly simple, but also surprisingly surprising. So the rank nullity theorem actually sort of tells us something that seems plausible when we think about it geometrically, but isn't really obvious. So let's think about the geometry of this. Now, to do this, we're going to interpret our matrix as a linear vector function from Rn to Rm. Okay, and just to have an example that I can draw, I have to choose pretty small dimensions, right? So R2 is going to be my stand-in for Rn, and R3 is going to be my stand-in for Rm. And I guess to draw a picture of R3, I'm going to draw a box, right? Because we can put vectors anywhere in this box, and they'll be in R3. Okay, and A is some linear vector function. So why is it that the rank of the image, so we're saying the dimension of the image of A plus the dimension of the null space of A has to be equal to n, right? This is the rank nullity theorem. So why does that make sense geometrically? Well, you're going to have to take my word for it a little bit, because we don't really know a lot about the geometry of this sort of linear vector function yet. But if you take my word for it, a linear vector function, so its image is a subspace, and that means its image maybe is a line. Okay? If the image is a line, then this dimension is 1. Well, what would the null space look like? Well, what linear vector functions do is they sort of squash things down onto some subspace. So this, essentially, what a linear vector function does is it takes some subspace of your, where you started, and it puts it into where you're ending up. So this linear vector function takes this red line and just sticks it over there. But what does it do to all the other vectors in Rn? Well, it has to put them somewhere. And so what it does is it squashes them sort of laterally, like this. And this is the part that you have to take my word for. So we will see later why this is true. But in fact, linear vector functions, if you aren't on the line that's getting copied over, you get squashed laterally onto that line. But if you look, there's one line of vectors, one line through the origin, that gets squashed onto the origin. Right? Most vectors don't get squashed onto the origin, they get squashed somewhere else. But there's a whole line of vectors that get squashed onto the origin when we do this squashing operation. So those are all of the vectors in the null space of the matrix. And if you look, the dimension of the null space, well, there's a line worth of stuff there. and the image is the dimension of the image is 1, but that's because the dimension of this red line is 1. And the red line and the green line, right, you have to fill up all of Rn, and in this case R2, because the domain of this linear vector function is Rn, or in this case R2. So something has to happen to every vector. So every vector is sort of a part that gets squashed onto the red line plus a part of the red line. Right? So everything, that's R2, has to be part of this one-dimensional stuff that gets squashed to 0 plus part of this one-dimensional stuff that just gets copied over into R3. So that's sort of the geometric version of the rank nullity theorem. It also explains why the rank nullity theorem, it's n that shows up. Right? The rank plus the nullity add up to n, and not m. It has nothing to do with m. And the reason is because, right, we did a lot of thinking about what happens in our starting space, but it doesn't really matter what space you're ending up in. All that matters is what is the image in that space, right? If it weren't R3 that we're ending up in, but instead R4, I would draw the same picture, right? Because the image is still a line, it's just sitting inside of a bigger space. The interaction between these two sizes is really all about what happens over here, and not what happens in Rm.